Hello, we are Group 1. Our project topic is 3D printed polymer foam composites for automotive crushbox. Crushbox is a component that is used to protect the front bumper beam and the side rails. The conventional materials used on this application is aluminum or steel. Some of the crushboxes are filled with aluminum foam in order to enhance the energy absorption performance. This aluminum foam could be manufactured by gas injection or investing casting method. However, these manufacturing techniques are complicated and consuming a large amount of energy. Furthermore, the structure of produced aluminum foam are always non-uniform, and this will lead to mechanical failure. The industry currently addressing this problem by using polymetric foams as the filler to replace aluminum foam. On the basis of this, we will plan to add carbon fiber into PEK to make further improvement. Carbon fiber PEK is selected to solve the non-uniformity problem of aluminum foam, but how the problem is solved? To achieve a better performance, the proposed solution should be able to withstand a higher crush force and absorb a higher crush energy than the current crush box design. Compared to aluminum foam, polymer foam composites are more lightweight, with high strength to weight ratio and energy absorption capabilities. However, there are only a few manufacturing methods available for carbon-filled PEK, including injection molding, extrusion, and thermoforming, all with limited use. Meanwhile, it has been proved feasible to produce carbon fiber reinforced high-performance materials using the 3D printing process. By incorporating 3D printing technology into the manufacturing of carbon-filled PEK, the team is expecting to see improvements in crush worthiness compared to traditionally used aluminum foam. Also, with the maturation of 3D printing technology, the complexity of the techniques are significantly lower than the conventional manufacturing method of aluminum foam. In case of material, we use CES software to compare the density and compressive strength of both material and to select the proper volume fraction of carbon fiber. As we can see, the PEK with 40% carbon fiber honeycombed structure has higher compressive strength and lower density among all materials. FDM is the most widely used form of 3D printing technology, and essentially it belongs to the material extrusion series. The process uses a filament-type thermoplastic with a print head that heats the filament to above its glass transition temperature. Fused deposition modeling prints 3D objects by building layers of material using heated filaments. The thermoplastic is heated to a semi-liquid state, and the layers are formed by an extrusion head on a heated printing bed. Let's talk about what FDM can bring us. One of the best gifts from FDM is high scalability, which means it can be easily scaled to any size. During the design process, by adjusting the previous computer-aided design modeling, FDM technology can perfectly make a delicate honeycomb structure, and the size of the cells can be adjusted according to specific needs. But the ability of scaling also causes some troubles. We will talk later. Another advantage is the flexibility of the material. The manufacturer can choose to simultaneously print a multitude of materials. This makes it possible to print complex models, since an additional print head can be used for support material. And it means printing with multitude of colors is possible too, as figure shown. The availability of materials ranges from commodity thermoplastic to engineering materials and high-performance thermoplastics such as PEK. Of course, the mechanical properties and the dimensional accuracy will be dependent on the type of materials used. Our group will mainly focus on elaborating the FCM process and the CF-filled PEK filament. Compared to injection molding technology, FDM is very time-consuming. Injection molding only needs to inject molten plastic into mold and wait for it to cool, while FDM technology requires frequent drawing of 0.1 or 0.2 mm layers to form the model. Also, fused deposition modeling lays down layers is just like a hot glue coming out of glue gun. This often leads to ribbing, and you can see lines from each layer. To remove these lines, an extra step of polishing or sanding is required. The slow manufacturing process results in high costs and undesirable productivity. In addition, FDM has strict requirements on ambient temperature, since temperature fluctuation during production could lead to delamination. Based on research and analysis on the features mentioned, in the crush box application, we decided to add FDM to the production line of automobile components. The construction material we choose is PEEK, which was produced by step growth polymerization. Nowadays, 3D technology is commonly used in automotive industry, and in some companies, FDM and 3D scanning technologies have been applied to the design and production of various components. For example, in October 2014, the world's first 3D printed car named Starty appeared in New York. The car is entirely made of carbon fiber and plastic, and it may be the first car in the world to be produced entirely by FDM technology. This further proves that this technology is feasible in an automotive application. In our crush box application, complex geometric designs such as a honeycomb structure optimize the weight ratio, which is hard to achieve with other technologies. In the production process, the use of decentralized production methods can reduce environmental impact and reduce production costs. 3D printing can do this while maintaining centralized coordination. For example, if a manufacturer intends to produce the same car at two locations, the design and parts of the car produced at each location are basically the same, but the processing and production processes are often different. This is a risk for manufacturers, but by utilizing 3D printing technology, manufacturers can distribute design ideas to the world through CAD files, thereby achieving a highly customizable uniformity. By performing ANSYS simulation, the mechanical performance of aluminum foam and 40% carbon fiber PEK are further analyzed and compared when applied with a range of forces. A 6 by 4 by 6 cm aluminum block with ordered cellular structure is used to simulate the impact on aluminum foam when an object crashes onto it. This figure shows the deformation of aluminum foam under a force range from 10 kN to 100 kN. The maximum deformation is calculated to be 12.154 mm, which occurs at an impact of 100 kN. To compare the proposed design with aluminum foam, a honeycomb-structured 40% carbon fiber PEK block with the same dimension is analyzed under the same force conditions. The figure shows the resulting deformation. As we can see, the maximum deformation is 3.9 mm and 100 kN. In conclusion, the deformation of PEK block under a range of force is 3 times smaller than aluminum foam block. The density of it is 27% lower than aluminum foam. Therefore, we consider honeycombed 40% carbon fiber PEK will have better performance than aluminum foam. However, there are still limitations to the 3D printing of carbon-filled PEK, mostly due to high capital costs and low production capacity. In the end, the team has come up with the solution of using 3D printed honeycomb structure 40% carbon fiber PEK to substitute traditional aluminum foam as the filler of automotive crush boxes. The performance of the selected material is analyzed by ANSYS based on material's physical and mechanical properties generated from the CES software, and the results proved that energy absorption capacity of the selected material outperforms the conventional material. Meanwhile, the proposed design is limited by high capital costs and low production capacity. Some future developments include validating the ANSYS simulation results experimentally and further confirm the dimensional parameters of the honeycomb structure.